For the past decade, we believed the future of electronic warfare would be fought in the electromagnetic spectrum. We built multimillion-dollar jamming systems, advanced radar arrays, and complex spoofing algorithms designed to tear down the invisible threads of radio frequencies. But today, the spectrum is dead. With the emergence of artificial intelligence, visual navigation, and autonomous target tracking, standard jamming has become obsolete. Modern drones no longer need GPS. They do not even need an operator. Faced with an impenetrable electronic wall, engineering did what it always does when the future fails. It looked to the past. The industry went back to wires. Right now, kilometers of single-mode fiber-optic cables are being unspooled in midair. They deliver unjammable, crystal-clear 4K video feeds through the most hostile airspace on Earth. But every physical solution creates a physical vulnerability. If you cannot jam a radio frequency, you must physically cut the glass. This is the engineering breakdown of the ultimate low-tech, high-science aerial duel. The automated ambush drone, codenamed Zhdun, and the kinetic cable cutter designed to hunt it, the Strum Blade. To understand the hunter, we must first analyze the prey. The drone known as Zhdun is an engineering masterpiece of passive denial. It does not fly patrols. It does not search for targets. It sits perfectly still in a state of deep technological hibernation on the roofs of buildings or along logistics routes, waiting for weeks. From a systems engineering perspective, maintaining a continuous standby state on standard lithium batteries is impossible. The idle current draw of a conventional flight controller and optical system would deplete a battery pack in less than 48 hours. To solve this, the platform utilizes a hardware-level sleep state configuration. The primary telemetry systems, speed controllers, and main processing units are completely isolated from the power supply via solid-state switches called MOSFETs. The only active component is an ultra-low-power optical sensor coupled with a hardware interrupt line. This is wake-on interrupt logic. The system draws less than 50 milliamperes. It consumes virtually nothing until the optical sensor detects a specific shift in the pixel matrix, indicating a high-value target. Once triggered, the electronic switch is close, delivering full current to the core architecture. Within 180 milliseconds, the system boots, initializes the motors, and takes off. And because it trails a microfiber optic line, it requires 0 radio handshakes. There is no signal to intercept. It is a ghost until the moment of impact. When a threat emits no radio signal, your defense grid cannot rely on software patches. It requires a physical response. Enter the Strum Blade, a high-speed interceptor engineered for automated infrastructure sweeping. Its mission is simple yet mechanically brutal. Fly over known logistics corridors and cut every optical line deployed in the airspace. The payload is deceptive. A high-tensile steel wire weighted by a calculated aerodynamic plumb bob, dropped beneath the chassis. But flying a stable quadcopter with a long, unspooled cable at 70 kilometers per hour is a nightmare of fluid dynamics. A cable hanging in still air forms a classic mathematical curve. But the moment the drone moves, air resistance takes over. The system is governed by the fundamental drag equation. Drag force equals 0.5 times the air density, times the forward velocity squared, times the aerodynamic drag coefficient of the wire, times the frontal area exposed to the wind. As the velocity increases, the drag force scales exponentially with the square of the speed. This forces the trailing cable to deform from a vertical line into a sweeping parabolic arc. If the velocity is too high, the cable rises too close to the rear rotors, causing catastrophic structural self-entanglement. To prevent this, the interceptor's flight control firmware must continuously run real-time state estimations. It dynamically adjusts the drone's pitch angle to compensate for the pulling force of the wire, altering the stance of the rotors to keep the kinetic cutter perfectly positioned in space. What happens at the exact millisecond of interception? A standard single-mode tactical fiber optic line, such as the G.657A2 standard, is incredibly resilient. It is engineered with an outer diameter of less than a millimeter, reinforced with woven aramid yarns, commonly known as Kevlar. It can withstand high tensile loads along its length without snapping. However, its weakness lies in transverse shear stress and stress concentration. When the high-velocity steel wire of the interceptor strikes the deployed optical fiber at an angle, the entire kinetic energy of the moving platform is focused onto an impact zone measured in square micrometers. According to classical mechanics, this creates an acute stress concentration factor. The local shear stress instantly exceeds the ultimate tensile strength of both the protective polymer jacket and the internal silica glass cladding. Before the glass fiber can even bend to dissipate the energy, it undergoes a critical structural fracture. The phenomenon is absolute. First, bending losses spike to infinity as the geometric boundaries of total internal reflection are destroyed, leaking the laser signal out of the core. Microseconds later, the physical link is severed. The target drone is instantly cut off from its command station, blinded, and neutralized. This is the reality of modern industrial and defense technology. No matter how advanced your artificial intelligence tracking models are, no matter how fast your board processors calculate data streams, your system is ultimately bound by the physical limits of materials science and structural mechanics. In the high-stakes arena of autonomous hardware development, the engineer who masters the physical constraints of the real world will always dominate the market.